Morning, everyone. My name is Robert Underwood. I'll be talking about scaling the AuroraGPT data pipeline with Parsl. For those of you who don't know, AuroraGPT is a large LDRD effort at Argonne, which is intended to really answer this fundamental question. Is a foundation model trained on additional scientific text and data more effective on scientific tasks? This could take various different forms. It could be more effective tokenization of domain science concept, better domain awareness for specialized domains, better support for scientific data modalities. But to answer any of these questions, we need to prepare a lot of scientific text and data. So I help co-lead a team along with Ian Foster that looks at this question of how do we prepare large quantities of scientific tokens. Here are some of kind of the key goals that we have been tasked with as the data team. I'm not going to talk a lot about the specific AI work that we do here, but what I will talk about is how that we've built nearly everything that we've done on top of Parsl. So we have 4 large codes that our group has put together. AdaParse, this is mainly Carlos Siepenschuk, data pipelines, which I wrote, LSH Bloom, which will be presented by Arham Khan later today, and Biodata Narratives, which was also written by Arham Khan in collaboration with some others, but he won't be presenting that. Also, in the context of AuroraGPT, we look at what are patterns in AI codes to understand what better services could be used there. Colmena has already been mentioned, but also Greg Pulowski will be talking about Academy, which is used in some of the codes that we reference here. Additionally, the AuroraGPT inference team uses Globus Compute, and Benoit will talk about that in a later session. So why Parsl? I'll keep this short and sweet. Simple Python-based futures designs, consistent code across laptops and HPC machines, scalable MPI backend for workflows, built-in checkpointing and resilience, and a substantial experience amongst our team. But what I did want to kind of do here today is I wanted to kind of present a series of lessons learned, things that we think that we can improve going forward in how we interact with Parsl. So let's kind of talk about a couple of bumps that we hit along the way. So the first one was that we tried initially in our first writing of this code, we wrote it in such a way that we'd loaded the AI model on each Python task. Well, the kind of thing to observe here is that because Parsl workers are generally stateless, what that means is that we would spend, in some cases, up to 50% of the runtime of each call just loading the model onto the GPU, compiling it, getting it ready for use. We'd use it for a relatively short amount of time, and then we'd throw all that work away when we go to launch the next job. So the fix that we ultimately used here was to modify Parsl to persist the GPU model so that it lasts between calls. This is essentially what makes Academy and things like Colmena interesting, is that they allow you to kind of have persistent state that survives individual tasks. It's a good context for using things like this. Another thing that we looked at is data compression and prefetching for some of the data that's involved. Plug, our group, when we're not doing AI, I do a lot of work personally on data compression. Another topic or kind of bump that we hit along the way was around the grain size and the overall performance. So when we started off, we wrote our code and it looked something like the code at the top. And inside each of these classes that's here in the Python, we had a series of Python apps that were responsible for doing all of the underlying work. The effect was that we had way too many jobs and way too little work to do in each of those jobs. So the ultimate fix was to kind of rewrite some of this code from this form above into more of a libraries style approach where we have a single @Python app that caches things and does checkpointing that handles kind of an arbitrary chunk size. And we'll talk a little bit more of that in a minute. But having this notion of the @Python app where we fused all of the operations dramatically improved the performance here. Now, some food for thought for this group and maybe for some others is I suspect that this is something that could be automatically done by the framework to try to figure out, like, this is how much time we're spending on average per task. If you had some way of knowing that a function was broadcastable or capable of operating on chunks in addition to operating on individual scalars, you could maybe try to auto-tune this a little bit. And then the worker could potentially change this. And then ideally, in such a world, the checkpointing implementation in Parsl would be aware of this and would have some notion of checkpointing that would checkpoint at a sub-task level, so that if your grain size changes because you move from your laptop to an HPC machine, you're able to leverage that same checkpoint information as you move forward into the larger system, or even just different numbers of resources on the same system. Another bump that we hit along the way had to deal with Parsl's checkpointing implementation. So the mistake that we made was that we returned our parsed set of papers as an object rather than as a handle to a file or a path to a file. So what this meant was that we were returning Python objects that, when they were pickled, were on the order of 2 to 3 gigabytes per object. Obviously, with that much data, some of the data flow graph concerns that we talked about earlier come to the forefront. But that's actually not the only problem that you hit. So the other problem that you hit is that if you combine this with Parsl checkpointing, that you very quickly get an out of memory error on the head node of your Parsl job. This led me to say, okay, well, let's move the execution of the Parsl job off of the head node and onto a compute node, where we now have much more memory available. We're not going to get killed by the system admins for using too much memory on the head node. That didn't solve the problem. So then the next thing is, oh, well, we're not cleaning up our futures. They're not getting garbage collected properly. That's why we're still running out of memory. So we go and rewrite our main loop of the code to make sure that we're deleting all of the references to the results. And at this point, we're still getting out of memory errors. So at this point, we're like, okay, what's going on? So we bring in this really useful tool here called Guppy3, which allows us to get a understanding of the Python heap and understand what's keeping these large, like multi-gigabyte strings still alive. And as it turns out, it's the checkpoint implementation. It's just forever holding on to a reference to this data, so it's just constantly leaking memory. This said, okay, well, let's see if we can fix that. So Yadu wrote a disk-based checkpointer that kind of wrote every individual task out to a pickle. I believe that Ben Clifford wrote a implementation based off SQLite as well. Ultimately, because there are other memory leaks in the checkpointing implementation, this essentially delayed but did not fix the issues that we had with taking too much space. So ultimately, what we decided to do is just write the outputs directly to disk inside the task and just return a path to where that information was on disk. This decreased us from using order of gigabytes per task to order of megabytes or even kilobytes per task, which got us past all of the out-of-memory errors that we had. Another thing that we used here is this notion of kind of debugging and profiling. And I wish I could say more, but I think Yadu just called time for me. So I will wrap up here, but suffice it to say, coming from like a C or C++ world into a Parsl world, there's a lot of opportunities to improve the completeness and the level of interactivity and ability to dig into details with kind of the performance and profiling tools, especially around things like GPUs. So I will kind of lead this as my closing point. So with that said, thank you everyone for listening to my brief talk. In short, some of the lessons that we learned with Parsl: mitigate large task startup times with state and compression. Using tasks and batches to reduce scheduling overheads is super useful. Improvements are needed to the checkpointing implementation to handle returning large objects. And there are opportunities for improved debugging and profiling in Parsl.